Namaskara, welcome to Tech Girl Kannada YouTube channel.
Recursive definitions. A sequence is an arrangement of elements of a set and order. There are two commonly used methods to describe a sequence, that is explicit method and recursive method. In the explicit method, the general term of the sequence is explicitly indicated. In the recursive method, the first few terms of sequence are explicitly indicated. The general term is specified through a rule or formula, which indicates that how to obtain new terms of the sequence. Explicit method means it will be already having the general term, and that there will be a general formula to obtain the term that are already known. Then consider the sequence E formed by all positive and even integers. Explicit method is like 2n. Then for the recursive method, you will have an equals to an minus 1 plus 2. This is the recursive method. An equals to an minus 1 plus 2. That is a1 equals to a1 minus 1 is 0. Plus 2 is 2. So a1 is true. For a2, for a1 is 2 and a2 is a2 is a1 plus 2. a1 is 2 plus 2 is 4. So that a2 becomes 4. This is the recursive method. So now obtain the recursive definitions of the sequence in each of the following cases. An minus 1 plus 5, that will give you an. A1 first we'll considering the a1, a2, a3, then we'll analyze the situation, how much it is increasing or decreasing. Then we'll form the recursive definitions. a1 5, a2 10, a3 15, a4 20, and so on. Since a1 is 5, an will be equal to an minus 1 plus 5. But for this, what happens is, second one is a1 is 10. a1 is 10, that is nothing but 3n plus 7. a1 is 10, a2 is 13, a3 is 16, a4 is 19. Then for this, what you have to do, an equals to how much it is been decreasing from there, from increasing from a1 to a2, it is plus 1. So an minus 1 plus 3, it is 10, 13. 13 minus 10 is 3. So we are adding 3 with the previous value, so that will get the an. Then for the starting value of the n is what? 3 1 is n is same. For a1 it is 10, that we have not mentioned. Until when it will be correct? When n is greater than or equals to 2. Until a2 it is correct. Then for next relation, it is an equals to n square. a1 equals to 1, a2 equals to 4, a3 9, a4 16. So what we have here is 3 5 7. This is nothing but we can also write it as, like, if we do the minus from a2 minus a1, we'll get the difference, right? The difference is 3. It is increasing, then it is increasing by 2. The difference is only increasing by 2. So for that reason, what we have to do, an, that is an plus 1 will be similar to an. But what is increasing, that we have to know. From a1 to a2, what increased? 3 increased and 5 increased. For this 3, 5, 7, what are these odd numbers? And the n starts from 1 here. So for that reason, 2n plus 1 gives you the odd number. 2n plus 1 plus an. This is the recursive definition. Then we have this a1 equals to 3, a2 equals to 1, a3 equals to 3, a4 equals to 1, 2, an plus 1 equals to 2 minus minus 1 power n plus 1. This is what they have given. 2 minus minus 1 power n plus 1. For this we have to find the recurrence relation. So what we have the difference? Well, first we'll find the reference, an plus 1 minus an. So 1 minus 3 will give you minus 2. Right, how is this minus 2 came? Let us write the general formula for that. That is an plus 1 is, since we have 0 as the beginning and since we have nothing as this, 2 minus an plus 1 equals to, that is 2 minus minus 1 power n. 2 minus 2 is already 0. So what we have is minus into minus will become plus. So that is why we will have this as minus into minus 1 power n plus 1 plus minus 1 power n. So that it becomes minus 1 is common in both. So minus 1, take it outside. Then 1 into minus 1 will be left. So that will be 1 plus 1. 1 plus 1 is 2. So 2 into minus 1 power n. That is the difference. So that we will add to the previous value. An plus 1 equals to an plus 2 into minus 1 power n for all n greater than or equals to 1. Then prove for any positive integer n, fi minus 1 by 2 power I is equals to 1 minus fn minus n plus 2 by 2 power n. Fn denotes the Fibonacci series. The Fibonacci numbers are defined by recursively by f naught 0, f1 is 1 and fn equals to fn minus 1 plus fn minus 2 for all n greater than or equals to 2. For n equals to 1 we will have f naught by 2 0 equals to 0. For f3 we will have, for f3 we will have this as for n equals to 1 we had 0. Then f3 is 2 because that is f1 f naught. Then the required result is the given sequence is true. For assume that required result is true for all n equals to k greater than or equals to 2. So what we do is considering this sigma I equals to 1 to k and applying the given equation on that. Sigma considering I equals to 1 to k plus 1 now, and fi minus 1 by 2 power I, what changes in the right hand side? It will be f of, since there is a k plus 2, we have to make it as It's the difference, that is normal f of, that is f of k is given as f of the sigma of k plus 1 is there. Now we have to find that for k, sigma I equals to 1 to k of fi minus 1 by 2 power I plus fk by 2 power k plus 1, that is given in the this thing. K plus 2 is there, so that can be resolved in this way: fk by 2 power k plus 1. So we will have this as 1 minus f of k plus 2 by 2 power k plus, that is already given in the above statement, fk by 2 power k plus 1. Then we will have f2 1 minus, we are taking 1 by 2 power k plus 1 as common, so that it becomes 2 of f of k plus 1 minus f of k, so that it becomes fk plus 1 minus fk plus fk plus 2, that becomes f of k plus 2 minus fk will be f of k plus 1 plus fk plus 2, that becomes fk plus 3, that is equal to 1 minus 1 by 2 power k plus 1 of k plus 3, that we found for of k plus 1. The required result is true for n equals to k plus 1. Hence, by mathematical induction, the given result is true. For the Fibonacci sequence f0, f1, f2, and so on, prove that. This is an important question. Fn function equals to 1 by root 5, 1 plus root 5 power by 2 whole power n, and 1 minus root 5 by 2 whole power n. So let us consider this for f0, since f0 is given, so we'll consider it for n equals to 0 and n equals to 1. f0 is this 0 and f1 is 1. We assume that the result is true for n equals to k equals to greater than or equal to 0. So we will have fk is this, and then fk plus 1 as same as the above, same statement we have to write also along by adding the previous statement, that is 1 by k, 1 by root 5. Since k plus 1 is there, you have to add this. Everything with substituted by k, and then k minus 1 substituted by k minus 1. Even here also you will find the same variety, that is first one is everything substituted by k, whatever they have given in the question. In the same way, everything substituted by k, then for k minus 1, k minus 1 is, that is k plus 1 minus 1 is k only. Then for 2 power I, we have given it as 2 power k plus 1. So that is added. Here also we have done the same thing. Then we shall take the common thing as k minus 1 in both the sides. First common thing is 1 by root 5, then 1 plus root 5 by 2 power k minus 1 in the both the sides. Then what will be left out? Since we have taken k minus 1 powers of this 1 plus root 5 by 2, one thing will be left here, that is 1 plus root 5 by 2, and plus there is nothing in the second object, so it will be 1 only. Then minus, from here also if we take the 1 minus root 5 by 2 power k minus 1 as common, we will have 1 minus 5 by 2 plus 1. So if we consider this, what we will have? Then if we add this 2 plus that one will be equal to 3 plus root 5 by 2, and then minus even here also if we add that 2 plus 1 minus root 5, that is 3 minus root 5. Then we are having now it as, then if we multiply and divide by 2 for 3 plus root 5 by 2 and 3 minus root 5 by 2, we will get that will be equal to your 1 plus root 5 by 2 whole power k plus 1 and 1 minus root 5 by 2 whole power k plus 1. The required result is true for n equals to k plus 1. Hence the mathematical induction, the result is true for all non-negative integers n.